Picture yourself walking near an ancient volcanic landscape and picking up a dark, glossy stone. At first glance, it seems like any other rock, but strike it against another hard surface and it behaves differently. Instead of crumbling into rough fragments, it breaks into razor-sharp edges that can slice with surprising ease. This material is obsidian, a naturally occurring volcanic glass. Long before humans understood what glass meant, they were already using it. Archaeological evidence from East Africa shows that early humans were working with obsidian hundreds of thousands of years ago, shaping it into cutting tools and sharp implements. But importantly, this was not a human invention. Nature had already been producing glass for an immense span of geological time. When lightning strikes sandy ground, its intense heat can melt and fuse silica-rich material into branching glassy formations called fulgurites. Meteorite impacts can generate extreme temperatures capable of melting surface rock. And when volcanic lava cools rapidly, it can solidify into obsidian. So glass was never something humans created from nothing. It already existed in the environment. The true breakthrough came much later, when humans learned to produce glass intentionally, rather than simply find it. That shift from using natural materials to manufacturing them was a major technological turning point. For a very long time, people shaped obsidian into tools and collected unusual glassy fragments without understanding what they were. Eventually, humans discovered that intense heat could transform ordinary raw materials like sand into entirely new substances with unique properties. That discovery began a chain of innovations leading from decorative beads to windows, mirrors, eyeglasses, scientific instruments, fiber optic communication, and even the screen you're looking at right now. But before we understand how that transformation became possible, we need to answer one fundamental question. What exactly is glass? Because the popular idea that glass is simply a liquid flowing extremely slowly is misleading. Glass is an amorphous solid, a material whose atoms lack the long-range crystal structure found in substances like quartz or salt. And that distinction changes how we understand it. Because once we look at glass at the atomic level, something remarkable appears. Humans learn to control a material whose atoms refuse to arrange themselves like those of ordinary crystals. So what actually makes glass different from an ordinary solid? The answer begins at the atomic level. Most solids we encounter have an organized internal structure. In crystalline materials, atoms arrange themselves in repeating patterns, almost like a microscopic lattice. Salt does it, ice does it, many minerals do it too. But glass behaves differently. When a glass-forming molten material cools, its atoms normally tend toward an ordered crystal structure. However, if the material cools without giving those atoms enough time to organize, the crystal structure can fail to form. Instead, the atoms become locked into a disordered arrangement before a repeating crystal structure can develop. The result is what scientists call an amorphous solid. It behaves like a solid. You can hold it, shape it, and break it. But internally, it lacks the repeating structure of a crystal. This unusual structure helps explain why glass can behave so differently from other materials. It can be transparent, it can be colored, it can be shaped while hot, it can form thick blocks or extremely thin sheets. And unlike natural volcanic glass, such as obsidian, manufactured glass can be engineered by changing its ingredients. But early glassmaking faced a major challenge. For many traditional glasses, the main ingredient is silica, or silicon dioxide. Pure silica requires extremely high temperatures to melt, far beyond what early furnaces could easily achieve. So ancient craftspeople needed a workaround. They introduced substances called fluxes. A flux lowers the temperature needed to melt silica, making the process much more practical. One important ancient flux was natron, a mineral rich in sodium carbonate. But alkali-rich glass could be chemically unstable, especially when exposed to moisture. So another ingredient was added. Lime, or calcium oxide, helped stabilize the glass and improve its durability. The basic recipe became surprisingly simple: silica for structure, soda to help it melt, and lime for stability. Humans already had the raw materials. The real challenge was discovering that heat could transform them into something entirely new. And that discovery may have happened accidentally while people were trying to produce something else. So how did humans first realize this strange transformation was possible? For centuries, a dramatic beachside accident was blamed, but the real story is far more complex and much older than the legend suggests. For almost 2 millennia, one story was retold as the dramatic birth of human-made glass. The Roman historian Pliny the Elder wrote about Phoenician traders traveling along the Mediterranean coast near the river Belus. According to his account, the merchants stopped on a sandy shore to cook. They placed blocks of natron beneath their cooking pots. A fire was lit. As the heat intensified, the natron supposedly reacted with the surrounding sand. When the fire died, the traders allegedly discovered glass forming across the beach. It is a vivid story, But there is a major problem. A simple open-air fire would not normally reach the extreme temperatures required to melt silica-rich sand into glass, even with a flux like natron. So Pliny's version is better treated as an ancient origin story than a scientifically reliable explanation. Archaeology tells a different story. Some of the earliest securely identified glass objects are small beads from ancient Egypt and Mesopotamia, dating to around the middle of the 3rd millennium BCE. Researchers have proposed several possible pathways for how glassmaking emerged. One leading idea involves faience, a quartz-based material widely produced in the ancient Near East. Faience isn't true glass, but its production involved heating silica-rich compounds with alkaline substances. Sometimes, surfaces partially melted and formed thin glass-like coatings. Over time, artisans may have learned to deliberately create and refine this glassy material. Another possibility connects glassmaking with early metallurgy. High-temperature furnace work could produce shiny, glassy slags as byproducts. A worker might have noticed their unusual appearance and experimented with how their properties changed when reheated. What becomes clear is that there was probably no single inventor of glass. Instead, the technology may have emerged through repeated experiments, accidents, observation, and gradual refinement across generations. Evidence of early glass production in both Egypt and Mesopotamia, along with chemical differences between them, even suggests that glassmaking may have developed independently in different regions. In other words, glass may not have been one invention. It may have been a possibility waiting to be uncovered wherever heat, minerals, and curious craftspeople came together. But even after humans learned how to make glass, it remained far from ordinary. For centuries, it was so rare and valuable that it belonged to the same elite world as gold, jewels, and royal treasures. Once humans learned to manufacture glass, they didn't suddenly begin producing it for everyday use. For centuries, glass remained a specialized luxury material associated with elite goods. During the Late Bronze Age, roughly between the 16th and 13th centuries BCE, glass was a high-status material exchanged among royal courts and powerful elites. That tells us something important. The challenge wasn't simply making glass. It was controlling the process. Raw materials had to be prepared. Furnaces needed to sustain extremely high temperatures. The mixture had to be carefully balanced, and producing a usable object required considerable craftsmanship. Early glass was valuable not only because of its appearance, but because it was technically demanding and often difficult to produce consistently. This becomes clear in diplomatic exchanges from Amarna, the short-lived Egyptian capital associated with Pharaoh Akhenaten. Correspondence between Egypt and other Near Eastern kingdoms shows glass among the luxury goods exchanged between courts. It wasn't treated like an ordinary household material. It was a diplomatic commodity. In some cases, the quality of glass shipments was important enough to become a point of complaint between rulers. Compare that with today. A drinking glass is inexpensive. A window is expected. A mirror is routine. But in the Late Bronze Age, a vividly colored glass object represented specialized knowledge, controlled production, and access to elite workshops. Amarna also provides evidence of organized glassworking. Excavations uncovered rods, ingots, colored glass fragments, partially finished objects, and furnace-related remains. Researchers believe craftspeople used a staged process. They could first create a partially fused material called frit. This was then crushed, processed, and reheated. A second melting stage helped produce more workable glass. It required careful control of heat and timing, remarkably difficult under ancient furnace conditions. These were early forms of high-temperature chemical engineering. And ancient glass connects to something even older. A famous scarab set into one of Tutankhamun's royal pectorals was made from yellow-green Libyan desert glass. This natural glass formed during an ancient high-energy event long before human history. It was already glass when humans encountered it. The material was later shaped and incorporated into a royal object, valued for its rarity and appearance. But even with all this skill, early glassmaking had one major limitation: hollow vessels were slow and difficult to produce. That would change when a new technique made glass faster to shape, easier to repeat, and far more widely available. For more than 1,000 years, making a hollow glass container was painfully slow. Ancient craftspeople had to build each vessel individually. One early method was core forming. A craftsman created a temporary core from materials such as clay and organic matter, attached it to a metal rod, and covered it with hot glass. The surface was then shaped and decorated while still hot. After cooling, the temporary core could be removed, leaving a small hollow vessel. These objects could be beautiful, but producing each one required considerable time and skilled labor. That kept glass expensive and limited its availability. Then, around the middle of the 1st century BCE, a revolutionary technique emerged in the Eastern Mediterranean: glassblowing. Instead of building a vessel around a solid core, a craftsperson gathered molten glass onto the end of a hollow metal tube. Then came the crucial step. They blew air through the tube. The trapped air expanded inside the hot glass, pushing the material outward into a hollow shape. By rotating the tube and manipulating the soft glass, craftspeople could create bottles, cups, jars, and other vessels far more efficiently than before. It was a simple idea with enormous consequences. Glass no longer had to be formed entirely through slow piece-by-piece construction. The material itself could be inflated. That meant vessels could become thinner, larger, lighter, and far more numerous. Production increased significantly. Although the technique and its economic impact spread gradually, the Roman world became especially important in expanding its use. Workshops across the Mediterranean produced containers, drinking vessels, storage bottles, and other objects on a much larger scale. Glass that had once belonged among elite luxury goods was becoming a practical commodity. Some craftsmen even became recognizable makers. One famous example is Ennion, a 1st century CE glassmaker whose name appears on mold-blown vessels found across parts of the Roman world. 2,000 years ago, a craftsman was effectively putting his name on products distributed across distant markets. Glassblowing didn't just change how glass was shaped, it changed who could own it. And once glass became more accessible, humans discovered another astonishing use for it. We had learned how to make glass quickly, but the next breakthrough was even more radical, using glass to transform the way humans experience their own buildings, windows. Once glass could be produced more efficiently, people discovered it could do something far more important than hold perfume or wine. It could let light through a wall. That sounds obvious today. But imagine living in a world where a solid wall meant darkness. You could open a doorway, make a hole, or live without daylight. Glass offered another possibility. You could close an opening against wind and weather while still allowing sunlight inside. The Romans were among the earliest societies known to use glass in architectural windows on a significant scale. Archaeological evidence from Pompeii, preserved by the eruption of Mount Vesuvius in 79 CE, includes pieces of Roman window glass. These early panes were nothing like modern windows. They could be thick, uneven, cloudy, and far from perfectly transparent. But they performed the essential function. They admitted light. That alone was revolutionary. Glass transformed the relationship between interior and exterior space. A building no longer had to choose completely between protection and daylight. As glassmaking improved, panes could become larger, clearer, and more consistent. Eventually, glass became one of architecture's defining materials. But ancient glassmakers could achieve something even stranger. They could manipulate glass at microscopic scales without understanding modern nanotechnology. One extraordinary example is the Lycurgus cup, a 4th century Roman cage cup preserved in the British Museum. In one lighting condition, the cup appears greenish and opaque. Change the direction of the light, and the same glass can appear reddish and translucent. For centuries, the reason was unknown. Modern analysis revealed the secret. The glass contains extremely tiny particles of gold and silver. Their interaction with light produces the cup's remarkable color-changing effect. The Romans didn't understand the modern physics behind it, yet they had created glass whose optical behavior depended on particles measured at the nanoscale. That is an astonishing reminder of what ancient craftsmanship could achieve through experimentation. Glass was no longer merely transparent. It was becoming a tool for controlling light. And once humans learned to manipulate light with glass, an entirely new technological world opened. The next step would not simply be letting sunlight through a wall. It would be using shaped glass to make the invisible visible. Because once humans learned to bend and focus light with glass, they gained something far more powerful than better windows. They gained the ability to see things their eyes could never reach on their own. By the 19th century, scientists were learning to control light in ways that would eventually allow glass to carry information. Glass had already moved far beyond being something you simply looked through. It was becoming a material engineers could use to guide and manipulate light. One important principle is called total internal reflection. When light travels through glass and reaches its boundary at a sufficiently shallow angle, it can reflect completely back inside instead of escaping. The light remains confined within the glass as it travels along its length. For a long time, this was mainly an optical curiosity. Eventually, engineers turned it into practical technology. The result was fiber optics. Instead of sending information only through electrical wires, pulses of light could travel through extremely thin strands of glass. Think about what that means. A message becomes patterns of light. Those pulses enter a glass fiber. They remain confined within the glass as they travel. Thousands of kilometers away, another device converts the light back into information. The glass isn't reading the message. It is simply providing an efficient pathway for light. This transformed communication. Modern fiber optic networks can carry enormous amounts of information across continents and beneath oceans. Internet traffic, telephone conversations, video, financial transactions, scientific data, all can travel as light moving through glass. And the material doing the work is still based on the same basic substance humans were experimenting with thousands of years ago: Silica. The difference is precision. Modern glass can be manufactured with extraordinarily controlled composition and purity. Even tiny imperfections can increase signal loss. Ancient craftspeople learned that sand could become glass. Modern engineers learned to control that glass so precisely that it can carry information across the planet. But communication wasn't the only field transformed. Optical fibers and miniature cameras could also be combined in medical instruments to look inside the human body without large surgical openings. The same material that once became beads in royal vessels had become a pathway into places human eyes could never reach directly. And this is where the story becomes almost absurd, because the material that began as a luxury decoration eventually became part of the invisible infrastructure connecting billions of people. But glass still had one more transformation waiting, becoming the surface through which we experience the digital world. Today, one of the most common places you encounter glass isn't a window. It's the screen in your hand. You touch it, swipe across it, watch videos through it, read messages on it. But underneath that familiar surface is an extraordinary combination of materials and technologies. Glass became essential to modern displays because it can be highly transparent while remaining strong enough to protect delicate electronics underneath. Modern display glass is manufactured with remarkable precision. Its surface must be extremely smooth, its thickness carefully controlled, and it needs to survive scratches, impacts, temperature changes, and constant handling. That is a very different challenge from making an ancient glass bead. Yet the material still has the same deep connection to silica and high-temperature processing. The transformation becomes even more interesting when glass is chemically strengthened. One important approach uses ion exchange. The glass is placed in a molten salt bath containing larger ions. Smaller ions near the glass surface are replaced by larger ones. That creates compressive stress at the surface, making the glass more resistant to certain types of damage. In other words, engineers aren't simply making glass thicker. They're changing its structure near the surface to make it tougher. This helped make thin glass practical for portable electronics. And once glass became a protective layer over displays, another revolution followed: touchscreens. The screen wasn't merely something you looked through anymore, it became an interactive surface. Your finger could communicate with the device through the glass. A material that once served as a passive barrier had become part of the interface between a human and a machine. Think about how strange that would have seemed to an ancient glassmaker. Their goal might have been producing a clear or colorful vessel. Today, glass can protect electronics, support transparent conductive coatings, display images, and respond to touch while remaining transparent. The material has repeatedly changed roles. Natural glass, manufactured glass, luxury objects, containers, windows, lenses, scientific instruments, communication fibers, and now interactive digital surfaces. But the basic ingredient didn't become magical. Our ability to control it became more precise. And if humans can engineer glass down to microscopic and even nanoscale structures, the final question is no longer what glass can do, it is what future technology might be hiding inside the same material we've been shaping for thousands of years. Modern glass has reached a point that would have seemed impossible to the earliest glassmakers. We can make it clearer, stronger, thinner, more chemically resistant. And in some cases, we can design it to respond to damage in ways ordinary glass never could. One research direction is often described as self-repairing glass, but the reality is far more limited and far more precise than the name suggests. We are not talking about a shattered window knitting itself back together. Instead, researchers are exploring materials that can respond to microscopic damage, especially tiny surface cracks that may be invisible to the naked eye. Ordinary glass is brittle. Once a crack begins, stress concentrates at its tip, allowing it to spread rapidly through the material. A small defect can become a catastrophic fracture. To address this, some experimental glass systems are designed so chemical reactions at damaged surfaces can reduce or partially close microscopic cracks under specific conditions. These effects are subtle. They do not restore a broken object, but they may slow or limit the progression of microcracks, helping extend the material's useful life. The key idea is not dramatic regeneration. It is damage management at the microscopic scale. And that represents a major shift in how humans think about materials. For thousands of years, the goal was simple: make glass, shape it, try not to break it. Modern materials science asks a different question. Can we design materials that respond to early signs of failure? That question has led to increasingly sophisticated glass compositions. Some resist scratches, others withstand extreme temperature changes, some conduct ions, others can interact with their environment in controlled ways. And glass is no longer limited to windows and screens. Specialized glass ceramics can survive rapid heating and cooling. High-precision optical glasses are engineered for telescopes, cameras, and scientific instruments. And bioactive glasses can interact with biological tissue, forming bonds with bone and supporting certain medical applications. What we call glass is therefore a broad class of amorphous solids engineered for different purposes. Ancient humans discovered that a hardened melt could be shaped by fire. Modern humans learned to control its chemistry, structure, and behavior with extraordinary precision. We can make glass that carries light across oceans, glass that protects digital devices, glass that reveals distant galaxies, glass that helps doctors see inside the body, glass that interacts with living systems. The material didn't become more powerful because nature changed. Our control over it deepened, and yet one limitation remains. Glass is still fundamentally brittle, so the real question is no longer how to make glass stronger, but whether combining it with entirely different materials could create something that no longer behaves like glass at all. The biggest weakness of ordinary glass is also one of its defining characteristics. It can be extremely hard. It can resist scratches remarkably well, but once a crack begins, glass can fail suddenly. That limitation pushed engineers toward a different strategy. Instead of asking how to make pure glass stronger, they began asking, what if glass could work together with another material? This led to several families of engineered materials, including laminated glass, glass composites, and glass ceramics. The goal isn't simply to make glass thicker. It is to control its internal structure so the material behaves differently under stress. One important example is laminated glass. 2 or more layers of glass are bonded together with a polymer layer between them. If the glass cracks, the interlayer can hold many broken pieces in place. This doesn't make the glass impossible to break. Instead, it changes what happens after it breaks. Laminated glass is widely used where safety matters, including vehicle windshields and architectural applications. The material becomes a system rather than a single sheet. Then there are glass ceramics. These begin as glass but are carefully heat-treated so controlled crystalline regions develop inside the material. The result can combine some advantages of glass with properties associated with ceramics. Depending on their composition, some glass ceramics have extremely low thermal expansion, allowing them to survive dramatic temperature changes without cracking as easily. This makes specialized glass ceramics useful in cookware, laboratory equipment, telescopes, and other demanding environments. But the fascinating part is what humans can now do deliberately. We can decide how much should remain amorphous. We can encourage microscopic crystals to form. We can add layers. We can exchange ions. We can introduce nanoparticles. We can alter the chemistry to control how light, heat, electricity, and mechanical stress interact with the material. Ancient craftspeople discovered a mysterious substance emerging from a furnace. Modern engineers can begin with a list of desired properties and work backward toward a carefully engineered glass composition. The material didn't simply become stronger. Our ability to design it became more precise. The ancient glassmaker was trying to make something beautiful. The modern engineer is trying to make something useful. But the next generation may be trying to make glass do something much stranger: sense the world around it. From a dark volcanic stone to the screen in your hand, the history of glass is really the history of humans learning to control matter. At first, nature gave us the material. Volcanic lava created obsidian. Lightning created fulgurites. Ancient impacts produced natural glass in deserts. Humans simply learned to recognize these materials and use them. Then came the bigger breakthrough. We discovered that glass could be manufactured. Sand, minerals, fluxes, and intense heat could be combined into something entirely new. At first, glass was rare and luxurious. Then craftsmen learned to make vessels. Glass blowing made production faster. Windows brought daylight through walls. Lenses expanded human vision. Telescopes revealed distant worlds. Microscopes revealed hidden ones. Eventually, glass became a pathway for information. Fiber optics now carry light across oceans. Optical fibers help doctors see inside the human body. Chemically strengthened glass protects the digital screens we use every day, and modern engineers can control its composition, surface, optical behavior, mechanical strength, and interaction with biological tissue. The real technological breakthrough wasn't simply discovering glass. It was discovering that glass could be engineered. For thousands of years, humans thought they were simply making glass. In reality, they were learning how to control matter with increasing precision. So, the next time you look through a window or touch your phone screen, remember, you aren't looking at a simple material. You're looking at thousands of years of human experimentation, discovery, and increasingly precise control over matter itself.